start recording. Good morning. It's Thursday already. I don't know how it happens, but it does. So let me just adjust some things here. Okay. I know the weeks are just flying by, and I don't know. Yeah, I was looking at my calendar, and I guess daylight savings is on the 14th. And it's the bad kind. Well, I mean, it's nice, but I don't like this one. Springing forward, no thanks. Yeah, losing sleep. No, not fun. But it means we're heading into spring, so I guess that's good. But yeah, it usually just like knocks me on my butt. All right. Enough about that. Let's see here. What did we do last day? Oh yeah, so we talked about some functions, and we talked about graphs of functions. Specifically, we talked about some common functions to recognize, right? Being awesome. Yes. Thank you, Sonia. I knew there was something. That I had said. All right, good. Yeah, I know. If Sonia's not here, I don't know what I'll do. Yeah. So we talked about some common functions like linear functions, kind of straight lines like this. We talked about power functions, which can kind of look like this or like this, depending on the situation, right? Here we have even powers, here we have odd powers, and we'll talk more about these, so that's why I'm kind of rushing through them. But we can talk about root functions, even roots, oops, sorry, kind of like this, even roots or odd roots. Notice these are just squiggles now, but kind of the general shapes, right? And so this type of exercise is what I want you to be able to do, right? If I say, oh, draw an odd root function, okay, then you know it goes like this, right? Draw an even root function like this, right? And so you have this kind of idea of what they look like. And then the reciprocal functions, which are like 1 over x, right? Or 1 over x to the n, where the n is either odd, making it look like this, or even, where they both go up like this. That one, I'm doing a little bit more of an explanation. And then, of course, the absolute value, which looks like a V. Nice. And then we talked about, okay, so graphically, we can identify functions, so whether a graph represents a function, if it passes the vertical line test, right? So a graph represents a function if it passes, well, that says parses if at best, if it passes the vertical line test, right? Meaning if we can draw a vertical line at any point and it only intersects the graph once, right? So any vertical line will only intersect the graph once, then you have a function. line will only intersect the graph once. It's kind of the Coles notes version. Okay, of course, we talked about it last day. So then for that, for testing purposes, I only throw that on for kind of like a gimme mark, easy marks. And so then I give you a graph and you tell me, hey, does this represent a function? Yes or no. You don't need to explain why, but it's good to get in the habit of saying, yes, it is a function because it passes the vertical line test. Or no, it's not a function because it does not pass the vertical line test, right? And so we'll have a look at some more functions, but I think that's pretty straightforward, right? Where you can draw a vertical line. Key is remembering what vertical is. A vertical line at any point, and it'll only intersect the graph once. And then we talked about the domain and range of a function. So the domain is the possible inputs, right? So possible values of x, and the range is the set of possible outputs, right? Which would be y, and I should say y or f of x, right? I want you to kind of get in the habit of reading those two interchangeably, y or f of x. So because I know f of x, when you read it, it can be a little bit boggy. So then if you just kind of in your mind read it as y, then all of a sudden things become easier. But y depends on an input of x, right? So y is a function of x, and that's why we would use this function notation. But for readability reasons, I like to just think of it as y. Okay? So here, if we have 2.3, we have this little guy here. So we've already talked a lot about the domain, right? We're going to keep talking about the domain. Domain is all the possible inputs that we could have, making sure you're not dividing by 0 or taking the even root of a negative number, right? And then the range can be a little bit trickier to think about because it takes into account the domain, right? So if you're looking at the domain, well, what possible outputs can I get from that domain? And that'll be the range. So as promised, let's do number 18. I'm gonna mark this up so I can bump it to the top here. So we're going to use a graphing calculator to draw the graph of f. Of course, we're going to use Desmos, and then we're going to find the domain and the range of this graph, okay? And so I want to use a negative function to show you what happens, right? But in general, when I see this quadratic here, x squared plus 2x plus 1, we know from that list of common functions, right, that overall, this is going to behave like an x squared. There might be activity in the middle, but it's going to behave like the highest power of x. And so it's going to behave like this parabola, right? And so, but the negative out front is going to make it pointing down now. Okay? And we're going to talk more about that, but the transformations is what that's called. But it just flips it, so now it's pointing down. Okay, so now I know what to expect when I go to Desmos, and that's a good skill to have, right? Knowing what to expect when I graph this thing. So let's see here, we get negative x squared. I'm just going to plug it in here. Negative x squared, of course, looks like a negative, a parabola facing downwards, okay? and then I want plus 2x plus 1. Okay. So a couple of key points that I want to grab here, right? This seems to be the maximum. If I zoom out, there's, and knowing how quadratic behaves, right? I know it's not going to dip up and go kind of down and then up. I know it's not going to do that because I know it's just going to behave like a parabola. So if I kind of zoom in here, there's some key points that I want to talk about here. Well, the maximum, right? Of course, the peak of this thing. This is also called the vertex, which we'll talk about later, but the maximum or the minimum, kind of that peak of a quadratic, is called the vertex. So the vertex is at 1, 2, right? So when x is 1 and y is 2, it crosses the y-axis at 0, 1, and then it crosses the x-axis at negative 0.414 and 2.414. Right, so I can grab this thing and kind of sketch it out roughly. It looked something like this. I know here this is at 1, 2. This was at 0, 1, I want to say, and this was at negative 0.4140, and this was at 2.4140, I want to say. Let's pretend that that's what it was. I don't know. Okay. For the domain, what's important, and what we talked about last day, is a parabola. It actually just keeps, even though it looks like it's kind of limited, it actually, if you wait long enough, it will go to positive and negative infinity. So the domain for this thing, for any parabola, is going to be the set of real numbers from negative infinity to positive infinity. So the domain here is from negative infinity to positive infinity. I'm trying to keep it on the same page, so it got a little cramped here. Okay. Now, the thing about the range is that, okay, well, especially if we just have a graph, then it's easy to see. In fact, it's probably not until Calc 1, maybe Calc 2 even, that I would expect you to kind of be able to calculate the range. We don't really do it. You can easily graph it, so then it's easy to see the range from the graph. There are a few times when you can kind of reason your way to the range. But looking here, right, I don't find that it's obvious to see what the range would be, right? Looking at the function, I don't see what obvious values of y I can get, right? But from the graph, it is obvious, right? So that's why I'm going to use the graph. So here, this was at 1, 2, and I am going to confirm that. Yeah, 1, 2. Hey, not to brag or anything, but I feel like I copied it out pretty good. So this maximum here is at 1, 2. So what does that mean? It means that the y values are going to go up to 2, right? Up to and including 2. So for parabolas, you can assume that it includes this endpoint. And so it's going to include this maximum, but then it's going to go down to negative infinity, right? All these y values are less than 2, right? And so how we're going to write this out is from the graph, we see that the range is from negative infinity up to 2, including 2. Okay. Just because here, this is the range. Okay. Nice. So from a graph, I expect you to be able to grab the domain and the range. Okay. Good. Oh, so the 2 here, because this is when x is 1, y is 2. And so 2 is the maximum y value here. And so it's going from negative infinity up until 2, including 2, and then it's less than 2 again. So then we say that the range is all the values from negative infinity up to 2 and including 2. Is that awesome? Good. Good, good, good. Okay, so more graph things that we should be able to see. So we can talk about inequalities. So when is one graph less than another graph? Okay, so let's see here. So if you have a function f and a function g, right? Of course, we have to name them different things. So why not f and g? So if you have a function f and a function g, these two functions are going to be equal to each other at the points of intersection. Okay? So here, the solution of the equation, right? F of x equals g of x. So the solution being, okay, what value of x makes f of x equal to g of x? Well, that's going to be the point of intersection, right? So where are these things equal to each other? Usually that's not that hard to think about, right? Where are they equal to each other? Well, they're equal to each other at x, because here at x equals a, for example, then they have the same y value, so they're equal to each other. Right? Same thing at b here. The one that's a little bit harder to think about is when is, for example, f of x less than g of x? So now you need to think about f of x is the outputs of f, and g of x is the outputs of g. So now you need to think about the y values in terms of f and g, right? So on this graph, right? So for this first value of x, g is less than f, right? Because here, let's draw these in kind of different colors. Here, f is this pink one, and I'll do, maybe I'll do kind of, because it's against this background here. And I'll do g, oh, that's a bad color, isn't it? Orange. Orangey, glad I didn't say banana. So here, right, what you need to do, okay, so G is this orange one and F is this pink one. So at each value of X, you'll be able to tell me which one is larger than the other one, right? And so here at, let's say, this point, G, so let's call this X1. At X1, G of X is less than F of X, right? And that stays true until they intersect, right? So you can pick any value here. And what I want you to do is just pick a value, one value of X, and then just go straight up. And so here, if you're, so at X1, oops, G of X1 is less than F of X1, right? The output of G at X1, which is the one I kind of made up here, is going to be less than the output of F, which is actually above here, right? Whereas let's make this X2. So then I want you to just kind of look at one value of X and say, okay, at X2, now it looks like F of X2 is less than G of X2, right? Just putting in whatever input I'm naming this thing, Okay, so g of x2 is now larger than f of x2, right? Or if you want to write these the other way around, that's fine. But I just wanted to talk about f and g. And notice that it has the same behavior up until the next point of intersection, right? And so after this point of intersection, things change potentially. In this graph for sure, right here, f of x becomes greater than g of x after b, right? And so that's just what we need to know for inequalities of functions. I do want to make a note here just to emphasize two functions are equal to each other at their points, potentially more than one, points in brackets of intersection. Okay. So let's just do a quick example. And of course, we're just going to use Desmos for these things. Remember when it has that little graphing calculator icon? We're definitely just going to use Desmos, right? So here, this, oh, sorry, it's lagging again. Right here, we use Desmos to graph this thing. Notice that for each part A and B, one is the equal sign and one is just the inequality, right? So we can use the same graph. And let's do 29. So what I've got here is I have 16x to the power of 3 plus 16x squared. When does it equal x plus 1? Okay, so first thing I want you to do is get an idea of what you expect this left-hand side to look like. Well, x to the power of 3, I know it looks like this, right? So I know overall it should have some sort of shape like this. X plus 1, I know is a linear function, so I'm expecting some sort of linear function with a slope of 1 and a y-intercept of 1. All right, so we can get a lot of information from just the functions themselves. But let's graph this out in Desmos to see what things look like. So we've got 16x to the power of 3. Make sure you step that down, plus, so you're not adding 3 plus 16, that would be a different function, plus 16x squared. That's going to be my first graph. And just like I expected, right, there is some activity here in the middle, right, in the middle there, but overall, the overall shape is like this. Okay, so that's good. And then x plus 1. Okay. And just like I expected, it's got a positive slope, so it's heading up in the positive direction. And now, right, let's talk about some points of intersection here. So I've got, okay, a dog that's driving me nuts today. We've got these points of intersection, right? So let's just graph this out so that we can talk about them. Oops. Okay. 29. I think it looked something. Let me just confirm that. Oh, no, at the origin. Sorry. Something like that. And maybe something like, now let me see here. Okay. So here, I've got x plus 1 in green, and then in blue, I've got 16x to the 3 plus 16x squared. And let's just put down the points of intersection here. This was at, now I can't remember, -1, 0, -0.25, 0.75, and 0.25, 1.25. Let's see if I can do it. Oops, sorry, -1, 0, -0.2575, oh, 0.75, I should say. And finally, 0.25, 1.25. Might have botched that. Let's see here. No, looks good. Okay, so I've jotted down the points of intersection. A little sloppy, but they're there, so okay. So now, for this first, for part A, right, I want to know where these two graphs equal to each other. Well, that would be at the points of intersection. So what we can do is, and I'm just going to do it the way that WebAssign usually wants your answers, as a comma-separated list, right? And so 29A, 16x to the 3 plus 16x squared is equal to x plus 1 at x equals -1, -0.25, and +0.25, right? And so those I dare say are quite easy to find, right? Where these graphs are equal to each other, just remembering that it's just the points of intersection. Okay. A little bit trickier to find where these things, so where is 16x to the 3 plus 16x squared, where is it larger than or equal to x plus 1? So it's allowed to equal x plus 1, which means I'm going to include those intersections, right? Not necessarily the case for 30b, for example, where I don't include those intersections, right? Then I can go up to the point of intersection, but not including the point of intersection. All right, so just keep an eye out for that slight difference. So in this case, we can include the point of intersection. So B, where is 16x to the 3 plus 16x squared? Where is it greater than or equal to x plus 1? Well, so here, by saying the x values, right, it doesn't actually matter which function I put them into. If I plug in 0.25 into either of these, this one's easier, then I end up at 1 plus 0.25 plus 1, which is the y value. So typically we only list the x values that yield the points of intersection. Yeah, because we can find the y values, but so it's a little bit redundant. So we only state the x values. Nice, but I should have said that. In fact, we only need the x values for the solutions. Good. So now I want to know, okay, and these inequalities are usually going to yield intervals, right? Because if I want to know where, and I'm going to highlight this because this is my blue function and this is my green function. If I want to know where is blue greater than or equal to the green, so for what values of x is the blue line, right, greater than or equal to the green line? So if I pick a value of x maybe here, right, then if I trace down, well, I hit the green one first, right? And so the green line, which is x plus 1, is larger than the blue line, 16x to the 3 plus 16x squared. So that does not satisfy the inequality that I want, right? Then I go past this point of intersection, right? So here they're equal to each other. So I can start here, and because that satisfies the inequality greater than or equal to. Then I pick a value of x kind of slightly off of it. And then I see that, okay, well here at this value of x, the blue line is larger or higher than the green line. So for this whole region, it looks like that inequality is satisfied, and then it's equal to each other at this point of intersection. But then I keep going, and it looks like, okay, now they've switched off. So from negative 0.25 to positive 0.25, x plus 1 is larger than 16x to the 3 plus 16x squared. But then after 0.25, they switch off again, right? And so here, what I see is, okay, here's where it's greater than, and here's where it's greater than. So greater than or equal to, we have the solutions are starting from -1, right? So at x equals -1, they're equal to each other, which is part of the inequality, right? If we didn't have greater than or equal to here, I would have a round bracket here, of course, right? So then from -1 up to x equals -0.25, inequality is satisfied, including -0.25. And then we said, okay, well, not for this little region here between -0.25 and 0.25, but then we pick it up again from 0.25 and up to infinity. So how do we link these up? We use a U. So from 0.25 up to positive infinity, which we close off with a round bracket. So here, I'll just add that the solution here is this. What I want to show you, and what can be confusing, is, and I haven't tested it out yet, but I'm just going from memory. I'm pretty sure I can put this whole thing in, but what Desmos, so into Desmos, but what Desmos does is it just gives me the solution, right? And I think we've seen it before, but let me just try it. So instead of having x plus 1 on its own here, I'm going to have, where is it greater than or equal to x plus 1? And then, but it might be hard to see. If there was another kind of gap, it would be hard to see. You'd have to zoom out quite a bit, and it can be hard to identify. But if you've got a good idea, right, like we just did, then you can confirm your intervals with Desmos, right? So I would use it for confirmation rather than getting the answers. So here it looks like going from -1 to 0.25, and then from 0.25 up to infinity, which is what we found. Okay? So just notice when you put in that inequality, it actually only gives you the solution. It doesn't actually draw the functions anymore. Good. So, let's talk about where is a function increasing and decreasing. And this is one of those nice intuitive things where if I gave you a graph, right, let's kind of go back here, let's draw on your intuition. If I give you a graph that kind of looks like this, maybe, okay, and let's take it one step further to the maximum and minimums too. So intuitively, we know where this graph is increasing, decreasing at a maximum or a minimum, right? And so just to confirm, right, what happens here? Well, here I've got a positive slope, right? So if you're thinking, okay, well, it must be increasing, it is, right? So just go with your gut here. It looks like it's increasing, it is increasing, right? And then at some point here at the maximum, right, then it starts to drop down. So then it's decreasing. And then we've got a minimum here, just like you thought. And before we go any further, I do want to talk about, okay, well, this is a maximum, right? But there are values that are higher than it, right? So we call it a local maximum. So that's just terminology that we should introduce here. So here we've got a local max, and here we've got a local minimum. Okay. In this region, we're increasing. And in this region, the graph is decreasing. Pretty similar to what we saw earlier, right? So at these local maximums and minimums, that's where it switches, right? So that's where it switches from increasing to decreasing or vice versa, right? So here, if we go along here, it's decreasing up until the minimum, and then it is going to be increasing again. How do you make a minimum? Well, you have to have this sort of behavior, right? You have to have a decreasing function, and then it has to switch to increasing, right? And so otherwise, you don't have a minimum, right? And so here it's increasing again. Oops. Good. Okay. So we know what these things mean, right? We can look at a graph and we can already identify these things. And so just trust your gut here. You know what these things are. We'll throw in the official definitions, but as long as you have it under control and you're able to tell me, so if I give you a graph and you're able to tell me where is it increasing or decreasing, that's good, right? So you don't need this definition, because sometimes I find that it can get a little bit confusing. So because we can always talk about it in terms of the outputs, right? So if f is increasing on an interval, if f of x1 is less than x2, f of x2, if x1 is less than x2. So that's just saying, okay, if I take an input that's less than another input, and the output is less than the other output, well, then I have this increasing behavior, right? So technically, this is what it means to be increasing, right? The first output is less than the second output, right? And then vice versa, if it's decreasing, then the first output is larger than the second output. But as long as you have this kind of intuitive idea of where it's increasing and decreasing, I'm happy. Okay, so don't overthink it. Okay? But technically, you can compare the outputs with the inputs and talk about increasing and decreasing. So same thing with the local max and mins. So let's just grab the definitions here. Maybe I'll make this bigger here. There. So we talked about local maximums and minimums. because we're allowing for our functions. So think about a parabola, for example. There is no maximum, right? Because it just keeps going and going. But if you think about, maybe a graph like this, right? Pretty similar to what we just drew, right? Then you're going to have multiple maximums, right? And so a maximum happens when we switch from a maximum happens when we switch from increasing to decreasing, right? And a minimum, any minimum, happens when we switch from decreasing to increasing, right? And you can kind of visualize that. We call them local max and mins because they don't have to be overall max and mins. They just have to behave like minimums. So if you zoom in, then in that region, it is the minimum value here, for example, right? So it doesn't have to be the overall minimum because this one is smaller than this one here, but that doesn't matter. We call them both minimums because they behave like that little dip. So we have the definition. Let's not bother talking about it too much because I think you have a pretty good idea of max and mins, what they are. Okay. So what I want you to be able to do from these problems is, and I guess I should grab the whole question. So for these problems, I'm going to give you a graph, right? Or I could give you a function. You would have to use Desmos to graph it, but often I'll just give you a graph and you'll have to tell me things like where are the maximums and minimums, so local maximums and minimums, and where is it increasing and where is it decreasing, right? So let's just grab one of these and see. Let's do maybe 45. Oops, weird color. So 45, and I'm just going to grab it and make it bigger here so that we can talk about it. In fact, I should probably put this on its own page here. Okay. There. Okay. So first thing I want to do is where do I have some maximums and minimums, right? So I'm just going to highlight, okay, I've got a minimum here. And we'll need to use our ordered pairs because I have this grid and I have, okay, 1 square seems to be worth 1 unit. So I'm left 1, 2, and so -2 and -2 seems to be that point, right? So we need to figure out what these points are so that we can use them. It might be, easy to forget about this little maximum here, but we do have a maximum here at 0, 0. And we've got a minimum here at 1, 1. And then we've got a maximum at 1, 2, 3, 1. Oh, sorry, it should be 1, -1. What was I thinking here? There. Crisis averted. Okay, so we've got maximums, local maximums at, and it depends on, the format of the question, but either at 0, 0 and 3, 1, or at x equals 0 and x equals 3, right? Those would be local maximums at 0, 0, and 3, 1. Or at x equals 0, 3. It just depends on how they want your answers, right? And they'll say as a comma separated list, which would be 0, 3, or as ordered pairs, which would be the full pair, 0, 0, and 3, 1, right? So then we can talk about local minimums. My dog's making weird noises. Hey, you can. She has wrecked her bed so much that she's blocked her own doorway. So she's mad about that. I'll fix it once we take a little break after this. So don't worry, I'm not awful. Yeah. She's just mad. So here, if we're talking about minimums, we're at -2, -2, but also at 1, -1. So at -2, -2, and 1, -1. Or if they want it as a comma separated list at x equals -2 and comma separated 1. I always find that it's helpful if you're able to kind of draw on the graph like I'm doing, right? Because now if I want to talk about, okay, so I'll start here. So it's decreasing, right? So I'll just use different colors here, right? So we're decreasing. And I'm just going to pick up all the regions where we're going to be decreasing here. There's 3 actually. Okay. Decreasing. And maybe I'll use a blue again because it's hard to see the orange. But so we're going to be decreasing. And we assume that, of course, this graph goes to positive infinity and negative infinity. And so we're coming here from negative infinity, and we're going to be decreasing up till -2. I'm not going to include -2 because that's the maximum. So it's actually not doing anything. It's not increasing or decreasing. But I actually don't know what the rule is. I would say it's not doing anything because it's actually got a 0 slope at this minimum. So I'm going to say it's from negative infinity, and I want you to do the same. Negative infinity up until -2, not including -2. And then it's decreasing again from 0 to x equals 1. So union 0 to 1. And then it's decreasing again from x equals 3 up till positive infinity. Okay. A lot of the domain has been covered here, right? We've only got a couple of holes, and so if you want to think about it like it must be increasing. If it's not decreasing, it must be increasing in those kind of holes. That's fine, right? I actually think it's easier to just look at the graph and just sketch it out. And so here it's increasing. It's increasing, okay, from -2. So I'm only talking about the x values. Okay, so we only need to talk about the x values from -2 up until 0, and then picking right back up again at 1 till 3. So it's increasing from -2 up to 0, joined up at from 1 till 3. And you can see that this region would fill in the gaps here, and then we've got the local max and mins at the points, so -2, 0, 1, and 3. And so our whole graph is covered. Right? Yeah, so you don't have to you don't have to talk about the y values usually ever. So especially for increasing and decreasing, we just talk about the x values that make those happen. Yeah. Awesome. For the maximums and minimums, it's possible they want the ordered pairs, so then you would have to give the xy combination, but otherwise, no, just the x values is good. Nice. Great. Okay. Well, now she's settled down. Let's talk about the average rate of change, and then we'll have a little break. How about? Because it's just a quick little section. Okay. Let's see here. You know what? It's so small. I'll put it on the same page. So 2.4 is the average rate of change. We've already talked about the net change of a function, right? And so recall the net change is f of b minus f of a, right? So where a is less than b. So recall that the net change f of b minus f of a is the change in outputs from a to b. And so from x equals a to x equals b, we have this change in output. So that's the net change. So now if we want to talk about the average rate of change, right, then we have to divide by the distance that we've covered, right, which is the distance from a to b. But you might remember that for distances, we have to do b minus a and technically take the absolute value, but we're going to drop that here. So the average rate of change, oh, that's 2.3 still. Do I even have it? Oh, it's not here. It's somewhere else. I think I'm better off just grabbing it. How about while I grab it, we take a little break until 9. I know. You get a break. You don't get a break. Break until 9 o'clock. And then I'll grab those other handouts, I guess. Okay, so it looked like, I'm so confused because I could have sworn I did it on the weekend, but the notes for the rest of the section, so 2.4 I think was on there, but 2.5, 2.6, 2.7, and 2.8, I just posted them now and I just grabbed them and brought them down. So we'll have them, but yeah, sorry about that. I really thought they were up already. Oh well. Okay, so, hey, now I'm looking at the wrong, skipped way ahead. All right, so now I have the 2.4 notes. And so the average rate of change is really just an extension of the net change. And so here, let's just grab this little guy here. So the average rate of change is going to be the change in y over the change in x. And so, of course, if you have f of b minus f of a, we recognize that on its own, this is the net change. That's the net change from before over the distance in x, which is b minus a, because a is going to be less than b, right? So to find that distance, we can just say that, okay, I'm just going to take b minus a. Right, if I ask you the distance between 2 and 5, you would say that distance is 3 by taking 5 minus 2, right? And so same idea here. And so the average rate of change is just going to be the change in the outputs over the change in the inputs. Okay, and so let's do just one example here. Okay, so if we have a function, right, doesn't matter what the function is, whether it's called f or r or h or g or h or f or g or whatever, it doesn't matter, because right now we're kind of comfortable with working with function notation, and whatever is inside the brackets should be the variable that we're working with, right? So nothing crazy going on here. So if we're given a function, we can determine the net change and the average rate of change between the given values of some variable. And so just to spice things up, let's do 16, because now we're talking about f of z, but notice that 1 minus 3z squared, we could just replace the z's with x's and it wouldn't matter, right? But just to get comfortable with kind of variables that are not x, let's do 16. So if I have 16, then I'm told that f of z is 1 minus 3z squared. In fact, maybe I should write this down below here for some more room. And we want from z equals -2 to z equals 0, right? So notice -2 is less than 0, right? And so in terms of my formula that I have up here, right, where the average rate of change is f of b minus f of a, remembering that a has to be less than b, right? And so let's just kind of map that out here. Oops, it's supposed to be a different color. So a is -2 and b must be 0, right? Since a must be less than, since a is less than b. Okay. So in terms of my net change, which is from the previous section, I think it was even 2.1 maybe. The net change is f of b minus f of a. And I guess we should make a little bit more room here. F of b, so my function is called f, so I don't need to change that. In fact, I get sloppy sometimes. Even if this was g of z, I would probably still use f of b minus f of a, even though it should be g of b minus g of a. But like I said, I get sloppy sometimes, and it's kind of no harm, no foul. So I want to evaluate the function at b and then subtract the function evaluated at a. That's the idea. So f of b, well, in this case, right, you have a couple of different options, and it just depends on how you like to write it out. So what you could do is you could say, okay, well, 1 minus 3b squared, and then minus 1 minus 3a squared. and then substitute in your A and your B, I'm just going to go straight to substituting in the values. So this is going to be the same as f of 0 minus f of negative 2. Okay. F of 0, and I want to keep these kind of separate visually, so 1 minus 3 times 0 squared minus 1 minus 3 times negative 2 squared. Okay. Good. So I'm just going to plug these in, and just kind of to visualize where each thing comes from, I use these square brackets, right? Especially because I'm subtracting, I need to remember to bring that subtraction inside the brackets. But otherwise, we're kind of hunky-dory. So I'm going to simplify this, and this becomes 1 minus 0, which of course is just 0, minus 1 plus 3 times negative 2 squared. So negative 2 squared is 4, right? Anything negative squared becomes positive. And so negative 2 squared is 4 times 3, which is 12. And then I think I skipped too many steps here. So let me just pull it back here. 1 minus 0 minus 1 minus, oh, I didn't do 1. 1 minus 3 times 4. There, I'll slow it way down. I should do that. So then this becomes 1 minus, and then I'll keep the brackets for a little bit longer, 1 minus 12. Good. Which is 1 minus negative 11. 1 minus 12 is negative 11. So then this becomes 1 plus 11, putting me at 12. So my net change is 12, which means my function is going to be increasing from an output of 1, or sorry, decreasing, I guess, in this case. F of B minus f of A, sorry. This is my output at the later point. So 1 is my output at B, which is my second point. Negative 11 is my output at the first point, A. So I go from negative 11 up to 1, making it a net change of 12. So now my average change, my average rate of change is going to be f of B minus f of A over B minus A. But, and I want to try to keep it on the same page here. I might be out of luck. F of B minus f of A, I just found is 12, right? And so here, this is my net change. Net change is 12. And f of B minus f of A, well, I know is 12, and then I said B was going to be 0, and A is going to be 2. Okay. So the distance that I've gone is from negative 2 to 0, which would make a distance of 2, right? So I've gone a distance of, and how can I'm going to bump this up just a line, because I can do that. So here, 12 is going to replace f of B minus f of A. And then just remember that B is 0 and A is negative 2. Oh, and B is 0 and A is negative 2. So then I get 12 divided by 0 minus negative 2, which is going to be 12 divided by positive 2, which is going to be 6. So that's my average rate of change, is 6. I crammed it in on this page here, my average rate of change. Is 6. Now your average rate of change can be positive, it can be negative, it depends on the net change, but because if the net change is negative, then you're going down, right? And so then you've got a decrease. The handout also talks about linear functions, but then the next section is on linear functions again. So let's just go to linear functions, which we have actually spent a lot of time talking about, right? And so section 2.5 will also be kind of a flyover section. So linear functions. A linear function, so now we've talked about linear equations when y equals mx plus b, for example, but linear functions have the form using f of x. So linear functions have the form f of x equals ax plus b, but of course, the slope is a and the y-intercept is b, so, and it depends on what field you go into, right? So in statistics, we like to use b subscript 0 and b subscript 1, and so ax plus b, but whatever is attached to the x is the slope, and whatever is on its own is the y-intercept, right? And so notice f of x equals ax plus b is the same as y equals mx plus b, right? This is the slope, so whatever is attached to the x is the slope, and whatever is on its own is the y-intercept. So just kind of get in the habit of just seeing, okay, if there's one x and potentially a y-intercept, right, so plus some constant, then you have a straight line and you know how straight lines behave. Okay? So let's see here. What I didn't mention in the other section is that the average rate of change for a linear function is just the slope, okay? So for a linear function, the slope of the graph of f and the rate of change of f are both equal to a, which is the slope, right? So a is the slope of the graph of f, which is the rate of change of f, which makes sense, right? If you've got a straight line, then it doesn't vary in the rate of change, right? It's going to be the slope is the rate of change. So the slope is the rate of change for linear functions, is all that's saying. And we're not going to spend a lot of time graphing linear functions, but remember and it wasn't that long ago that we did linear functions, right? It was just as we came back from reading break, and we talked about things like, okay, well, what does it mean for two lines to be parallel and perpendicular, and what does it mean for the slopes, right? And so we've kind of dissected straight lines. Now we're just using f of x as our notation instead. That's the only change here. And so we still know about the slope and we still know about the y-intercept, And in order to draw a straight line, right, we need to find 2 points on the line, and then we can connect them with a straight edge, and then we've drawn the line, right? And that is because the average rate of change, or sorry, the rate of change, shouldn't say the average, I don't think, although I think it's true as well, because then you're dividing by the distance, right? So it depends. But the rate of change of a linear function is the same, and that's why we're able to just draw it and extend the line. So let's see here. So there are lots of different problems here, which I'm actually going to skip because we already did it very recently, so we don't need to do it again. But so determine whether the given function is linear, right? And so if you're able to rearrange things into the form of y equals mx plus b, then you have a linear function, right? And so whether you talk about f of x or y, it actually doesn't matter, right? And so the next section, right, so here, can you rearrange it into y equals mx plus b? Yes, then you have a linear function. Here, you can graph functions by finding different values. So you can plug in values of x and find the value of y. And maybe this is a good one. This is maybe the one I want to do. For this section. So for the given linear function, make a table of values and sketch its graph. What's the slope of the graph? So here, we're going to make a table of values to figure out what this graph looks like. And no one likes fractions, right? And so maybe let's use 17 just for some extra practice. Also because it's using a name other than f and a variable other than x, right? So the name is r and the variable is t, but it doesn't matter. So r of t is -2/3 times t plus 2. A couple of things I can already see, right, and you can already see, is that, okay, well, it looks to be in the form of y equals mx plus b. Right, so good. I can say that this is a linear function because I've got a t here. So instead of an x on the x-axis, I've got t, but nothing really changes. The slope is going to be -2/3. So I'm expecting this kind of downward relationship. And the y-intercept is at 2. So here, I've got a slope of -2/3, and the y-intercept is +2, right? So what does that mean? It crosses the y-axis at y equals 2, right? Or x equals 0 and y equals 2. Okay, so we're going to make a table of values and sketch its graph. Okay, so what you want to do is you can put in any value of t, right, because t happens to be our variable here. You can plug in any value of t and then solve this function, right? What's the output if I put in t equals 0, for example? Well, t equals 0 should be the y-intercept, and in fact it is, right? And so then we have our first point on this graph. You can put in any value of t. You just want to make sure that you pick one. If you're given a grid, for example, you want to pick a value of t and input that you have on your grid, otherwise it's hard to draw. So I will maybe first draw, I'll first draw a quick grid here. Okay, so here I've got t and here I've got r of t, right? But they behave the exact same way as x and f of x, or f of x is y, right? So nothing's really changed. And what I want to do is, because it told me to make a table of values, and if you ever have to sketch a graph, then you can always make a table of values. So what that looks like is I'm going to set up, okay, I've got t, and then I've got r of t equals -2 over 3t plus 2. So I'm going to plug in a value of t, and then I'm going to evaluate that value of r of t at whatever t I pick. So my first one, I always just plug in 0, right? It's the easiest thing to do. And so I always just use 0. And you can pick any value. But usually I tend to pick convenient values, right? So kind of easy values to deal with. So now I want to evaluate r of 0, right? What is the output when t is 0? So this becomes -2 over 3 times 0 plus 2, which is +2. Okay. So in terms of, and then usually on the side here, I just summarize it as my ordered pair. So in this case, I've got a point at 0, 2. And if I just kind of make fake little grids here, I've got 1 and I've got 2, and then maybe 1, 2, 3, something like that. My first point here is at 0, 2. Okay. Remember, we need 2 points in order to draw a straight line. Okay. So what am I going to do here? I've got this nasty fraction that I don't really want to deal with. I see I have 3 in the denominator. Okay, so what I'm going to do is I'm going to pick a t, a value of t that's a multiple of 3, because then I can cancel stuff out, right? And you know what I'm going to do is just having a quick glance. What happens if I put in t equals 3? Well, -2 over 3 times 3 is -2. -2 plus 2 is 0. Okay, so that's good, right? But what I want to do is, and I guess we can do that one. So if t is 3, then I get -2 over 3 times 3 plus 2, which we said was 0. So now I'm at 3, 0, which means I'm going to cross the x-axis there. That was a little too easy, I think. So another one that I want to look at is maybe if I extend this line, maybe if I extend it 3, 4, 5, 6, right? What if I did 6? Okay. So now I'm going to let t be 6. Then I see -2 over 3 times, 6 plus 2. 6 divided by 3 is 2, and then -2 times 2 is -4, and then plus 2 puts me at -2. So here I'm at -2. So now I've got a third point at 6, -2. So now I'm going to use 6, and then -2 would be down here somewhere, right? Only because I've got a page break here, so. Yeah. So it doesn't matter which value you put in here. You could have put t equals 1 in here, but then you've got -2 over 3 plus 2. You have to add fractions, right? So you need a common denominator of 3, and it just gets a little bit messy, and then it's hard to draw. So pick convenient values of t here. But then we're able to draw a line. So you take a straight edge, and I usually just kind of take a piece of paper, or even if we were in person, you would just take your page and just kind of not fold it over, but lift it over and use the straight edge of the piece of paper. But for now, let's see here. I want to keep it on this page. So it does keep going here. I just didn't want it to overlap. Good. So kind of a refresher on drawing straight lines, but other than that, right, so here, right, if we have the slope, then we also have the rate of change, right? The rate of change for a linear function is the slope. So let's go back to the question. So for the given linear function, make a table of values and sketch its graph, what we just did. What is the slope of the graph? The slope of the graph is -2/3. Of course, you could do it by picking values of x and evaluating the output, but we know that the slope is -2/3. So done. Kind of a weird section, right? Because we've already done this, so it feels weird, but good. Okay. Let me just make sure that I'm not skipping anything important. Nope. It's all fun stuff, but it's all review. So right ahead to 2.6. And the reason I want to kind of zoom through to 2.6 is because I want to introduce 2.6 so that we can kind of start off on the right foot next week. So 2.6 can be a little bit tricky. I'm not going to emphasize it too much, but there are some key things that we need to know. So 2.6 is on transformations of functions. Okay, so transformations of functions, we already saw that if we have a negative out front of our quadratic, then it actually flips it so it's facing down, right? So we have already seen that -ax² plus bx plus c flips our parabola, and so it's facing down, right? And the new addition here is this negative. We've already seen that taking the negative of the function flips the parabola, so it is facing down. Okay, so that's what we call a transformation. And so there are a couple of things that we can have happen, right? So if you have an original function, then it can move up, it can move down, it can move to the right, it can move to the left. It can even get squished or kind of stretched out, and it can get squished vertically or stretched out vertically. So there's a lot of stuff that can happen. And so just like we know those default functions, right? Quadratics, we know root functions, we know reciprocal functions, we know what their shapes are. We need to say, okay, well, this is a reciprocal function, but it's been lifted up by 2 points, for example, right? And so we need to know these transformations of functions. I'm not going to focus too much on it, but I will kind of on a test, I'll give you a function and then ask you, okay, how has this function been transformed, right? And then usually it's multiple choice and you just need to pick the appropriate one. So just need to pick the appropriate one. Harder than it sounds. So let's see here. First thing we want to talk about is just the vertical shift. Okay, so we can have a vertical shift. So first thing we're going to assume, and you would anyways, is that c is greater than 0. Otherwise it makes it weird, right? If you add a negative number, it's subtracting. So we're just going to assume that c is positive. So if you have a graph f of x, now in these scenarios, I want you to imagine f of x is that core function that we've talked about, right? Whether it's a linear function or usually a quadratic or some sort of polynomial, or a reciprocal function or a root function, right? So imagine f of x is that core function. If I add c to a core function, then it shifts it up by c units. Okay, same thing if I subtract c, which is a constant, then it shifts the whole thing down c units, right? And so here, f of x, and maybe I should draw the whole. F of x is one of the core functions we introduced in section 2.2. Right, so it's going to be one of those. Typically, there are other functions, but in general, right, for our purposes, it's going to be one of those core functions, and now we're shifting things around. So we can have vertical shifts. Vertical shifts behave the same way that you think they're going to behave, unlike horizontal shifts. So, or at least in my mind. So if you think about, oops, wrong section. So if we think about horizontal shifts, right? At least for me, when I think about horizontal shifts, when I see x minus c, well, in my mind, I want to shift the whole graph over, but that's what I mean. So it's actually counterintuitive to at least how I think about it, right? And so if I have x minus c, it actually shifts the graph to the right c units. And to me, that's counterintuitive. If that makes sense to you, then that's great. But I just, for me, I have to remember it as the opposite of what I want it to do, right? And so notice that the manipulation here is on the x, not the f of x, right? And so here, notice the manipulation, oops, spell it in the right order. Manipulation is on x, not f of x, right? So if you're manipulating f of x, that's when you get these vertical shifts, which makes sense, right? F of x is your y, so it's going to affect your y value. Here, for horizontal shifts, right? So horizontal shifts, horizontal is on the x-axis, right? And so now we're manipulating x to make a move horizontally. And just however you want to remember it, if you subtract c from x, then it shifts it to the right by c units, versus if you add c then to the x, then it shifts it to the left c units. And to me, it's counterintuitive. If it makes sense to you, then that's great. Okay. So the difference between vertical transformations and horizontal transformations are going to be, is the f of x being manipulated or is the x being manipulated? So let's write that down. Vertical transformations are manipulations on f of x. Manipulations on f of x, since f of x equals y, which is the outputs, on the vertical axis. Right? In general, manipulations on f of x behave the way that that we want them to intuitively. I'm not going to write that down because intuition is, it might be different for you, but for me, it behaves the same way that I want it to when I just think about it. So horizontal transformations do not. Horizontal transformations are when we manipulate the x inside f of x. So, or when we have manipulations on x inside f of x. And I'm not going to write it down, but they typically behave the opposite of what you think they are going to. Okay, so let's have a look at an example. Let's look at this little guy here. We can do a combination of vertical and horizontal shifts. Okay. And typically what happens is we'll start with our core function, right? So I'm going to refer to those, that little blue box of functions that we introduced as our core functions. We start with a core function, and that's why it's so important to know how the root of x, what it looks like, right? So the root of x starts at 0, 0, and then it's got this kind of upward kind of bow thing going on. Okay. So then if we wanted to ultimately graph the root of x minus 3 plus 4, well, then we need to build it up to that, right? And so to graph f of x equals the root of x minus 3 plus 4, we need to start with the core function f of x equals the root of x, and then build up to the bigger function, right? The transformed function. And then slowly, I'll say in quotes, build up to the transformed function. But the key is to see, okay, if I want to graph this big function here, then I see at its core I have the square root of x, and that function has been manipulated. So now what I want to do is I want to say, okay, so I need to build this thing out. And so my first step is so step 1 is that f of x equals the root of x becomes f of x equals the root of x minus 3. Okay, because I can't just do +4. I mean, in this case I can, the order doesn't matter, but in the future it's going to be important that we kind of build up from the inside. Okay, so here I've got f of x minus 3, right? I've replaced my x with x minus 3, which is the same as f of x minus 3. And here, this is where I struggle at least, because this is actually a right shift, right? A shift to the right by 3 units. So we just take that root of x and we just shift it over to the right by 3 units. Shift the graph of f of x equals the root of x to the right by 3 units. All right, and it's important that we kind of put the brakes on and say, okay, it has to be to the right. So that means that, and what we can do, if you actually had to draw these out, right, I would pick kind of easy points to follow along. And so you can keep that shape by just kind of grabbing maybe this point and maybe this point, and then just follow those along, right? Shift all those x's over to the right by 3. Okay. Here they've already done it, and it's not something that I'm going to get you to do, right? We can use Desmos to check our work, but just being able to identify, okay, that the first thing is to shift over by 3 units to the right. Okay. Then to kind of bloom out, what we have to do is we have to say, okay, so here, this is my graph of the root of x minus 3. That's close, but not quite what I wanted. I want the root of x minus 3 plus 4. Notice that this plus 4 is outside of the root, right? And so that is the original function plus 4, which means I'm going to shift it up by 4. So step 2 here is that f of x equals the root of x minus 3, which equals f of x minus 3, depending on kind of if you're talking about the original function or if you're renaming your new function as f of x. We have to add 4, and maybe I shouldn't call it f of x anymore. It just gets confusing, doesn't it? And maybe call this g of x. Right? Let's not use the same letter again. Okay. So then, by the same kind of idea, let's call this h of x. These are our go-to function names, f, g, h. Okay. So h of x is going to be the root of x minus 3 plus 4, which is really the same as the original function, f of x minus 3 plus 4. Okay. So we bloom things out. So this means I have to shift the graph of, now I'm shifting the graph of the root of x minus 3 up 4 units. So shift the graph of the root of x minus 3 up 4 units. And yeah. So here, notice that 3, 0, right, got shifted up to 3, 4. And so here we could have followed this point 0, 0. Well, 0, 0, if I shift it over 3 units, becomes 3, 0. Right? And then if I shift it up 4 units, it becomes 3, 4. So that's what's going on here is you can pick points if you have to. You know, we will never have to. But if you had to, you could pick some points here and kind of follow them around in your transformations. Okay, so what I want you to do is for next day, I'm not going to pick one to use as review, but I do want you to read the rest of 2.6 just to have an idea of what's going on. So, oh, it clumped out. Okay. So 2.6, it's quite a long handout. The first 2 pages are what we will be covering, and then the rest is for practice. So here, I'll just write in. First 2 pages are required, I guess. And then the next 2 pages, last 2 pages are for practice only. Okay. So what we have talked about, right, is that we can have vertical shifts, we can have horizontal shifts. And then what we'll talk about is, okay, you can reflect graphs, which we've actually seen, right? If I take the negative, then it reflects it on the x-axis. You can reflect on the x-axis, or you can reflect on the y-axis, right? So what does that look like in terms of our function? And then we can talk about vertical stretching or shrinking, right? Same thing as horizontal stretching and shrinking. How does that happen in terms of our transformations? And then just briefly, I'll talk about even and odd functions. We don't need to talk about it too much, but even functions, right, have that kind of symmetry, whereas odd functions, if you think about x to the power of 3, would be an odd function, and it's got, you know, kind of something similar to this shape here. And then the rest is just for optional enjoyment. Okay. So I want you to read through that so it's not the first time that you see it when we go through it next week, because it's a lot of stuff, and we're gonna have to go a little bit quickly because a lot of it is just memorizing, or at least making your cue cards or kind of your cheat sheets so that you have all this information on there, okay? For the tests. Are there any questions? If you have questions, let me know. If not, I will see you on Tuesday, and I hope you have a great weekend. Awesome.